So this is the Particles Homework Booklet question 8. First up, we're asked to describe how the strong nuclear force between two nucleons varies with the separation of the nucleons, quoting suitable values for separation. So the key points here are from 0 up to about 0.5 of a femtometer. That's given in the specification, 0.5 of a femtometer. The force is repulsive, and then it's attractive from around 0.5 of a femtometer up to about 3 femtometers. The marks, in fact, were for initially repulsive, then attractive, and then for suitable values in the range of femtometers. For this switchover value, from where it goes from being repulsive to attractive, they accepted anything between 0.1 and 1 femtometer, but since 0.5 is given in the spec, please do give that. I think that would be the only safe answer. Obviously, we need the strong nuclear force to be repulsive at very short distances to stop the nucleus collapsing, and we need it to be attractive at greater forces in order to overcome the electromagnetic force of the protons repelling each other. An unstable nucleus can decay by emission of an alpha particle. State the nature of an alpha particle. An alpha particle is made up of two neutrons and two protons. They did accept it's made up of a helium nucleus. Some of you will know that's a pet peeve of mine. I think it's only a helium nucleus if it's part of a helium atom, and given that it doesn't have a couple of electrons and never has had a couple of electrons whizzing around it, I'm not convinced it's a helium nucleus, but we can certainly agree it's made up of two neutrons and two protons. Then we're asked to complete the equation to represent the emission of an alpha particle by uranium-238. So we start with the 238, 92 uranium. The key thing in here is to know that alpha has got 4 nucleons, 2 neutrons, 2 protons together make up my 4 nucleons, and a proton number of 2 because it's got 2 protons. Then all we've got to do for the thorium that we're given is to work out what these numbers are. By balance, I've got 238 nucleons, 4 of them end up in the alpha, so there must be 234 left in the thorium, and I've got 92 protons, 2 end up in the alpha, so there must be 90 left in the thorium. Finally, we're given that this uranium-238 decays in stages by emitting alpha particles and beta minus particles, eventually forming 206-82 lead, which is a stable isotope of lead. First of all, state what is meant by isotopes. Always same proton number for isotopes, but different nucleon numbers or different numbers of neutrons. Standard answer there. If there are 8 alpha decays, more complex question, 8 alpha decays involved in the sequence decays from the uranium-238 to lead 206 lead, deduce how many beta minuses are decayed. So first of all, I just had a quick look, make sure I had this right in my head, had a quick look at the nucleon numbers. Going from 238 to 206 is a drop of 32, so that would be 8 alphas, as we've seen. Remember, the beta decays don't affect the nucleon number because we change one type of nucleon, a neutron, into another, a proton. So what would that do to the proton number? Well, on its own, each time I do an alpha decay, I drop the proton number by 2, as we saw in the parts of the question above. So we'd be going from 92, and then I'd be taking off 8 lots, because I know I've got 8 alpha decays, 8 lots of 2, and that turns out to be 76. So on its own, those 8 alpha decays would have reduced the proton number down to 76. We're told that we don't end up at 76, we end up at 82, so I've got to find another 82 minus 76, that is 6 protons. Well, each time I do a beta decay, I gain 1 proton. So taking the proton number up requires a beta decay, so I need 6 lots of the beta decay. 6 beta decays required to get us from that proton number of 76 up to 82, remembering again that beta decay we see a neutron turning into a proton, and so we raise the proton number. So that's the Particles Homework Booklet, question 8.